So with this video, I'm hoping that you can gain some confidence into handling cis-trans problems that you may encounter on like a homework assignment or quiz or an exam. And to do that, I'm going to just have some questions here that are all cis-trans related. And I think the best approach for you is trying to learn or master this topic is to try to answer the question on your own. And what I'm going to do is, after you think you've completed the question, is play the video, and I'm going to walk through what I think about mentally when I approach a cis-trans question. And I think when you hear that over and over again, the way I approach it, you will really feel confident in your ability to handle any cis-trans question. Again, if you haven't seen the previous video where I talk about cis-trans and how to determine whether a molecule is in cis or trans for alkenes, check out that video. So for this one, there's the question. Go ahead and pause it, see if you can answer it, and then come on back and I'll walk through the answer. When you have a question like this, the first thing I'm going to need to do is we have to think about what the question is really asking us and realize what it's asking is there a molecule known as cis-3-hexene and a molecule known as trans-3-hexene? So it's not asking me to draw any of those or anything like that. It's just asking me, do they even exist? So for that, we got to go back to our knowledge of this. Since they're both, whether it's cis-3-hexene or trans-3-hexene, they're both 3-hexene, meaning they have the same molecular formula, which is the first step in making sure something might be an isomer or not. The second one is because they have the same name, that indicates it also has the same connectivity of atoms. So all we're really trying to do is understand, are there two different ways to spatially arrange the atoms in 3-hexene? So the first thing I'm going to do is go ahead and draw it. And when I go ahead and draw that, I'm going to draw a little bit different than you may have drawn it. But I like to start with the alkene part of it, because notice it ends in -ene, so it's an alkene, which again, alkenes can have cis-trans isomers, alkynes cannot, alcohols cannot, and so forth. And I'm going to go ahead and number the carbons as well. So I'm going to know that carbon 3 and carbon 4 in the molecule, because it's 3-hexene, meaning the 3 is where the double bond starts. Now I'm going to add in my other carbons as well, and I'm going to do it in a kind of a weird way, because since I know I like the double bond to look sort of like an X when I'm looking at cis-trans problems. It just helps me a lot. And so I'm going to go ahead and draw carbon 5, H2, and carbon 6 on that end. And then I'm going to have carbon 2, and carbon 1 would be way out here. And so there is my 6 carbons, because it's a hexene. So there's the 6 carbons, the double bonds on the third carbon, and then each of these carbons need a hydrogen. So I drew it in sort of that shape there because that represents its structural, more representative of its actual structural three-dimensional look. Very flat, looks kind of like an X, sort of, when you draw it. And now I'm going to go ahead and determine whether these can have cis-trans isomers. So to determine that, what I do is I look at one of the carbons in the double bond. So I'll take a look at carbon number 3. And when I look at that, the question I'm asking is if the substituent, or the group, the two groups attached to carbon 3, the hydrogen and this ethyl group, notice those are different. If I look on carbon 4, the hydrogen and the ethyl group are different. If both carbons involved in the double bond, meaning carbon 3 and carbon 4 in this case, if each of those carbons have two different groups hanging on them, we're not comparing carbon 3 and carbon 4. All we're doing is taking them individually. We look at carbon 3, they're different. We look at carbon 4, they're different. If both are different, then yes, they have cis-trans isomers. So the answer is yes, that 3-hexene does have cis-trans isomers. go ahead and give this one a try. Draw cis 3-hexene. Actually, that is what I've done here. What we've drawn here is actually cis 3-hexene. We know it's a 3-hexene, we just drew it. But the question is it cis or trans? So remember, to do that, what you do is you draw the railroad tracks through the carbon-carbon double bond, and then look to see where the two hydrogens are located. Notice here's a hydrogen and here's a hydrogen. Notice they're on the same side of the tracks. They're not one's on one side of the train tracks and one's on the other side. They're on the same side of the track. If they're on the same side of the track, that's cis. If they were on opposite sides of the track, that would be trans. And so the structure we had drawn there was actually cis 3-hexene. Now go ahead and pause the video and give this one a try. So for this one, once again, I'm going to go ahead and draw the structure of it first. And so once again, I'm going to go ahead, because I see that it's an alkene, and I know alkenes can have the possibility of having cis-trans isomers. I'm going to go ahead and move on, and I'm going to go ahead and draw that carbon-carbon double bond. And because the carbon-carbon double bond is on the second carbon, I'm going to go ahead and mark that as 2 and 3. And then I need 6 carbons total in my chain because it's hexene, and so I'll go ahead and do that. There's carbon 4, which is attached to carbon 5, which is attached to carbon 6. And I'm going to need one more carbon at this end for carbon 1. So there's my 6 carbon chain with the double bond on the second carbon. I also need to add in my substituent, and so on the second carbon I also need a methyl group, and so we'll add that here as my methyl group attached. And then on carbon 3, since there's no other substituents, that's just going to be a hydrogen. And so here's the question: are there cis-trans isomers of this molecule? And so once again, I'm going to go ahead and go on through and look at each carbon of the double bond individually, separately, to make sure that the two groups are different. And if both groups have different if both carbons have different groups attached to it, it does have cis-trans isomers. And so I'm going to start with carbon 3 here. So carbon 3, what does it have attached to it? What are the two groups? It has a hydrogen, and it has this propyl group, and those are different. And so we move on to carbon 2, and attached to carbon 2, we have a methyl group and a methyl group. They're the same. Carbon 2 has a methyl group and another methyl group. Those two methyl groups are the same. And so because one of the carbons of the double bond has the same groups attached to it, in this case, there are no cis-trans isomers. So notice, even though one of the carbons, carbon 3, did have two different groups on it, both carbons must have two different groups on it for there to be the possibility for there to be cis-trans isomers, which is exactly what we saw in question 1. Both carbons had different groups attached to them, so therefore they had cis-trans isomers. Here's another question to try, and then when you're ready, come on back and we'll walk through it. So this is nice because this now is going to get you to draw one of them as opposed to evaluating whether it can have cis-trans isomers. Now we're actually going to draw it. And so we have to draw a specific one this time, as we've done before. And so let's go ahead and give this one a try. So again, notice I see that it's an alkene, and the carbon-carbon double bond is on the 2 carbon extending to the 3rd carbon. And so I'm going to go ahead and draw that. And that'll be carbon 2 and carbon 3. It's pent, so it's 5 carbons long, so we're going to go ahead and do that. There's carbon 4, and that's attached to carbon 5. And so there's those. I want to get this into cis conformation. There's a couple ways I could do this, but I'm going to go ahead and put one of the hydrogens up, and the other one's going to have to be on the other side of the tracks. Whoops, I'm sorry. It's going to have to be on the same side of the tracks as that hydrogen. Remember my tracks. If I use this line, there's my railroad tracks going through the carbon-carbon double bond. I got to get to be in cis, I got to get the hydrogens on the same side of the track, so I got that there. And I also need to add in another carbon here. Carbon 1 has to be added as well. I have to now go back and add in my substituents. I got 2 bromine groups. One is on the 1 carbon and one is on the 4 carbon. So on the 1 carbon here, I'm going to have an H, and a Br. So I wrote that showing all the bonds. And then on this one, I'm going to go ahead and erase this stuff on carbon 4 because there won't be 2 hydrogens. There's only going to be 1. And I'm going to go ahead and put an H and a Br on that one. And so now I got a bromine on the 1 carbon, a bromine on the 4 carbon, and I have a pentane there. It's 5 carbons long. I got the hydrogens on the same side. It's in cis. And so that would be the way in which we could draw that molecule. Now, you may not have drawn it that way. You may have drawn it more in a straight carbon chain. So I'm going to show you a second way that would be just as equally good to draw if you'd like. And it helps us understand cis-trans isomers as well in the way in which we display them or show them on a piece of paper, since it's hard to get three-dimensional shapes on a two-dimensional plane. Let's go ahead and walk through this. Notice I can see that this is an alkene. It's got 5 carbons, and the double bond is on the 2nd carbon. So what sometimes I do is I'll start by drawing 5 carbons. There's carbon 1, carbon 2. The double bond is there between 2 and 3. There's carbon 4, and there's carbon 5. I got some substituents. I need a bromine group on the 1 carbon and a bromine group on the 4 carbon. And so I'm going to go ahead and put a bromine here and a bromine out here. It doesn't matter if I put it below or above. It makes no difference. I just stuck the bromines on there. And then also, carbons 2 and 3 each have 1 hydrogen attached to them, because notice they each have 3 bonds to them. So we need 1 more bond to them. We need a 4th bond to them. I need to put those hydrogens in cis. And so the way to do that in a linear fashion is just put them, in this case, like that. Both of them are up, so they're both on the same side. They're both above. I could have easily have done it just the other way as well. I could put both of them down. That would also be cis, because they're both up or both down. They're both doing the same thing. What I can't do is draw it like that. That would be trans, because I have one of them's on one side and the other one's on the other side. So that would be a trans model. We don't want the trans model. We want the cis model in this case. And so I'll just put them both down. And then I got to make sure I decorate the rest of the molecule with the hydrogens, since I've added all the substituents and I got my hydrogens in cis. There we go. There's our molecule there. So this molecule I drew here and the one I just drew previously are exactly the same ones. Again, this bromine here, that's right here, I could have switched with this one. It doesn't matter either way. And this bromine here, I could have put here or here. It doesn't matter where I would have put that bromine either. And those hydrogens would have filled in wherever the bromine wasn't. Give this one a try, and then go ahead and pause the video, and then come on back and we'll walk through this one. So when I look at this one, the first thing it's asking, are these not isomers at all? Are they cis-trans isomers, or are they actually the same molecule? So to do that, we can start checking out a couple things. Let's first see if they're isomers of each other. And to do that, they have to have the same molecular formula, which they do. They each have 3 carbons. They each have 2 bromines, and they each have 4 hydrogens. So they have the same molecular formula. The connectivity is also the same. If we look at one of the carbons is attached to 2 bromines, and that's true in both of them. And then the next carbon of the double bond is attached to one hydrogen and one methyl group. So the connectivity of atoms is also the same. Are they cis-trans isomers? They're not cis-trans isomers, and let's walk through that. I can tell because when I look at one of the carbons of the double bond, and I've circled that carbon that I'm looking at, notice the two groups attached to it are the same. And so that right there tells us they cannot be cis-trans isomers. So I know these are not cis-trans isomers, that's for sure. Because they have the same molecular formula and their connectivity is the same, and they're not cis-trans isomers, they're not even structural isomers, and so they're not isomers either. They're actually the same molecule. And to kind of show that to you, again, trying to understand three-dimensional structures on a two-dimensional plane is sometimes very difficult. But around those carbon-carbon double bonds, it's very flat. And so if you look at this structure on the left here, pretend it's a merry-go-round, and you're going to turn the merry-go-round 180 degrees. And when you turn that merry-go-round 180 degrees, you'll see the bromines will then line up, and you overlay it with the structure on the right. You'll see the bromines will line up, the hydrogen will line up, and that methyl group will line up, indicating it's the exact same molecule. So for the final question, I have this one. It's really the same as the previous question, except I just put two different molecules there. So give this a try. Come on back and we'll walk through it. So if you look at this molecule, again, you'll see that the molecular formulas are the same. So that means we could have isomers on our hands, or we could have the same molecule on our hands. The connectivity of the atoms are also the same. If you look at one of the carbons in the double bond, it's connected to a chlorine and a hydrogen. The other carbon in the double bond is connected to a chlorine and what looks like an ethyl group. And then, of course, the ethyl groups are going to be the same. And so the connectivity of atoms is the same here. And now what about if we look at each carbon of the double bond? We see if we look at this carbon, notice it has two different things attached to it. And if we look at this carbon on the left, it also has two different things attached to it. So this is an indication that these are cis-trans isomers of each other. And so the correct answer here would be cis-trans isomers. So these two molecules are cis-trans isomers of each other. And so that would answer the question. What you might be wondering is, well, which one is cis and which one is trans? Because I'm drawing the railroad tracks through the double bond. I'm circling the hydrogens, but there's only one. There's not a second hydrogen. So what do I do here? How do I know if it's cis or trans? Well, that wasn't the question, so you didn't have to answer that part. But it leads into a deeper rules of cis-trans isomers. Now, some of you might be not needing to know any more depth of cis-trans isomers, and so this might be good enough for you. For those of you who think you need to be able to talk about and learn about these guys, check out the next video because it gets into a little deeper understanding of cis-trans isomers, and this has to do with the EZ system of cis-trans isomers. So that's where EZ nomenclature comes into organic molecules, and really all it is EZ is just an offshoot of cis-trans. Thanks for watching. Hopefully this was helpful to you. Please comment, or if there's other things you want to see, please comment below, and we might be able to make a video of things that you think would be helpful for you to see. Till next time.